So I figured out what P and S means. Okay, so yeah, I'm very happy to take part on this occasion and congratulate somewhat belatedly Sergey and Kobe, whom both of whom I know for more than 30 years. Yeah, Sergey from our years in Novosibirsk, where even when Sergey was undergraduate in logic group in Novosibirsk, and Kobe I met in 1990. Well, actually, probably it was already January. Oh no, it was January 1990 when there was a logic year in MSRI, and Kobe was a graduate student then with Leo Harrington, and he came to me, and we started talking about what can be done in O-minimality in this context of trichotomy, and by the time there was a result by my informal graduate student Zhenya Rabinovich that a few years ago Asaf Hasson with Piotr, I think, with Piotr, they rewrote this in a more readable way, and so it was a case that dealt with similar situation in the sense that you already are in some geometry, you are inside algebraic geometry, and then you try to recover the field which you were, and we discussed this a bit. Right. So, so today I will talk of something that is close to my current interests, but what is remarkable that my current interest shifted towards what was going on in O-minimality. In particular, I do richly refer to work on Petrusov and Starchenko on the complex kind analysis in O-minimal setting, and then so what I'm discussing is okay. I go straight to the subject. So this is the situation that I'm trying to understand in model theory terms. So classical situation with where you have a complex analytic setting, and this is the simplest situation with complex analytic setting. So what you see here on this picture, it is you have something. So you have this. Anyway, so you have here some algebraic variety, and then there are finite covers of this variety, and you go up, and on the top you can find out that everything is covered by some nice complex manifold with some nice assumptions on it. And of course, the covering map would be some practically classical analytic functions. And so there have been this long-going attempts to digest this situation, to take it into model theoretic setting. Yeah, so you see that the simplest example, and this is really example that we started with, is just the case of exponentiation. And what I wanted to show here in this picture by adding this gamma. Sorry. How I move? Oh no. How do I move back? Is this? Oh, yeah. Thanks. You see, originally we have just this picture, and of course, saying that this is algebraic variety, I meant that there is key predicates on it, and because of these predicates, we can recover the underlying field. So, in this part of the structure, there is everything that we need in the language of fields. This slide with some additions shows also that actually we recover here more structures. So, for example, we have so the group gamma on the top is the fundamental group of this X, and it can be recovered from interpreting finite groups acting on finite covers. And when you go up, you in this Grothendieck profinite thinking, you get a profinite limit of this group, which is the same as profinite completion of the topological fundamental group. And you see, we can look at this picture in two ways. So one way, which probably Grothendieck introduced into algebraic geometry, is to think about this picture, to think about the structure on the top as being projective limit of what you see at the finite levels. And then it is a profinite object, well, a kind of a profinite object. And it is nice, but you lost analytic, the connection with the analytic world. And so my real, my aim is to understand what happens in the analytic picture. And so it is different from the profinite picture. Although it should be said that profinite picture is being used in this analysis very much, because for the same reason that profinite picture is a just projective limit of what you see here, you can embed this complex structure U with whatever structure on it is of interest to us into the profinite. So it is part of it. But model theoretically, we can quickly say what is the main difference between the two. So when you are in the profinite structure, then it is not saturated in full, but it is rather saturated. So all one type, well, positive one types, they all realize there. And you would have, of course, uncountable many of them. But in the analytic picture, it is very far from being saturated. It is really, so we can throw a look at the kernel, for example, kernel of exponentiation. So in the analytic picture, kernel of exponentiation is just the integers times 2 pi I. And in the profinite picture, it is z hat. And so you see that a lot is omitted. And so the problem is how to formulate model theoretically theory of this that tells you exactly which type should be omitted and which should be kept. Right, so going on this, along this path, it is actually, this story started sometimes in 2000, and there have been a number of theorems proved. It is actually a story of case studies. And so I try to not to forget any of the names involved in here. There is another branch of this story where we want to think about one sort of structure where the top and the bottom can be seen inside the same structure, and then you have a full exponentiation acting on algebraically closed field, which is a field of complex numbers, and then Shanou's conjecture is heavily involved in it. And so I don't list people here. So for example, Angus did a lot of work on in this setting. Okay, so what is the main outcome of this is that conjecture that you can write down an L omega 1 omega theory, and indeed very natural kind of set of axioms in the language of L omega 1 omega, which gives you categorical description of this situation. And of course, being categorical is well, some people say that I'm always it is just my habit to talk about categorical, but there is a good reason I think for it. It is first of all in this setting, in such an abstract setting. This is in fact the case of completeness. So for first of the languages, we have well-working notion of complete theory. And so for abstract elementary classes, if you say what is a completeness in this case, and saying that it is categorical, of course, it is the best form of completeness you can have. But another reason for this is that we also know from experience and from general theory that categorical comes together with a lot of geometric evidence that well, it brings stability and so on and so forth, which we all know is very important.
So, but if you fix one of these functions like exponential,
yeah,
then you already know the theory, no? I mean, it's the theory of the exponential.
In what sense you say I know this theory? Well, I know, for example, that it is a homomorphism from the additive structure to the multiplicative structure. But well, one thing that okay, then if you try to end up with this axiom, right, and just say just say that, for example, kernel of exponentiation is just the integers. Yes, this is a good guess, but to prove that it is categorical, you have to use the theorem about Galois action on torsion, which in case of C star, I mean, in the case of the multiplication, is a classical result of 19th century. But say in the case of elliptic curves, it is a hard theorem of Serre. It is open image theorem of Serre. And in the case of J function, it is something that took a long time for us to sort out, to extract. So it is very heavy loaded arithmetic facts that you use, but it is not all that we need to know. It is well understood now that there is this theory of well, let me just say this, that the latest results we now working with. I didn't want to go there, but we're now working with Chris Doe on the full version of for the J function, and it actually required us to learn the proof of Langland's conjecture on conjugation of Shimura varieties, and this Langland's conjecture on conjugation of Shimura varieties, it is indirectly, but it is connected with his Langland's program, and even to formulate this conjecture, it is a long paper, and a subtitle to this paper is. He uses a German word for this, ein Märchen, which means a fairy tale. So he was so sort of impressed by the beauty of the picture that you have to understand to. So it is a lot of arithmetic facts that you need to prove that your natural axioms like these ones satisfy. But for elliptic curves, for example, and it becomes much harder for abelian varieties. It is partially known, and yeah, for many cases it is. Yeah. Okay. So somewhere on this route, we have to stop and. Let me just end this story. So you see, one lesson from these case studies is that a proof of every such fact actually not only requires you to know these arithmetic facts, but you realize that the statement of categoricity of this particular L omega 1 omega sentence implies strong arithmetic results. And so at some point, well, you start asking yourself and maybe other people, So what is this, story between model theory and arithmetic? Whether going further along this route, we can somehow adapt model theory to produce maybe, if not new arithmetic facts, but at least a good arithmetic conjectures. And so on. Well, I'm not, so my talk today is not about this, although it is an interesting question, and it's more or less what I just said, that probably doing model theory in this spirit is trying to get another vision of arithmetic behind this. But it becomes very quickly, it becomes very difficult arithmetic business. And then there is a second question that from some point on, after your initial examples and this a little bit naive reaction that you have straightforward natural axiom and just try to prove that it is categorical. So now let's say that we don't care about how we axiomatize, whether it is a natural set of axioms or even whether it is even L omega 1 omega axioms. It is it becomes just a question whether this sort of class of covers that we can lift to supposedly we should be able to lift it to any cardinality. Well, simply just making your algebraically closed field bigger and bigger. Whether such a class can be made, can be seen as an abstract elementary class, which is categorical. So we don't care about the method of axiomatization, but the question and whether in this way we can state and prove general enough theorem that goes beyond concrete cases. So the answer to this is yes, the second question, and that's what I'm going to talk about. So actually, it turns out that the solution to this question is to embed yourself into some or minimal environment. And so what I'm doing here is that I'm considering an minimal expansion of the reals, and this would be the choice for each situation of the cover. So each complex algebraic variety, it has its own cover, and it would require its own minimal expansion of the reals, which seems to be quite obvious that you need. So for example, for exponentiation, it is more or less straightforward, and so on. And so we have some minimal expansion that I write like this. And in this minimal expansion, I have this algebraically closed field that is made of these non-standard reals. And I then have to assume certain quite natural assumptions, and these are as follows. So I have something that you can think about as fundamental domains for the corresponding U is the covering sort. So it is this complex manifold from where you go down. And so it is the open subset inside this complex manifold. And we have one for each level of the structure. You see, so for example, in fact, as you go up, you have to shift your original fundamental domain and glue together as many as the level you go up is. Right, so we have these fundamental domains which are definable in our minimal structure, and as you see, they are indeed well. Actually, the numbering between fundamental domain and yeah, I think I might have made it too complex. Never mind. Let's just assume that the fundamental domain that you need is starts from the same index as the one that you covers, and then you also need that there is this well, essentially in say in the case of universal cover, it is just we are talking here about topological fundamental group, which of course goes down and becomes finite deck groups, and then we require that that our picture with its n levels is complete in the sense that well, that the intersection of all gamma i's goes down to trivial, is trivial. Okay, so it is something natural and technical, right? Oh, yeah. Yeah, I think I have a slide where it says explicitly, but let me just say it now in this part. So where I get my examples of this. So these are, in fact, the only one I know are provided by Petrozil and Starchenko, well, except for exponentiation and, of course, very classical cases. So you really need to know something about existence of these conditions, but now for some very good reason, we are already deep in this business, and we have quite a few interesting examples of this. And so now I go from this minimal environment back to the construction of on my universal cover, and now I introduce the language that corresponds. So I call it L sub AEC. Then I seem to drop this subscript, abstract elementary classes. So now I'm thinking of taking a reduct of this rich language to a language that to a language that will eventually work in the setting of abstract elementary classes. And well, now you see, So what I defined here is a very natural thing. You just take the risky closed subset on algebraic levels. You take the inverse limit, and clearly it is going to be some analytic sets in the complex setting, and the intersection of analytic sets are analytic sets. And that's what we take to be the primitives of our language on the top, top.
So little k is a subfield of
yeah, little k. Yeah, this is. I don't have time to discuss this, and indeed, in the paper, I just introduced all the necessary. Yeah, so little k is the base field over which the base variety is defined, and this is quite interesting also to understand. For example, elements of gamma will be. Okay, they are sort of they correspond to types, and the types. What field you need to define this complete type? I mean, complete in this profinite setting, and so there is a certain interesting bookkeeping that links definability in the analytic language with definability in algebraic language. Yes, so little k is a field of definition. Right. So now I explain how I can look at irreducible components of these analytic sets that just have been introduced. So I don't know, maybe in the end, so a little picture could help. It's so if this is my U, and so here this one is say analytic curve that is lifted from some algebraic curve downstairs, and so I have my definable open subsets, and because it is so minimality, then in each open subset, this splits into finitely many components. But then I can take a bigger subset, and I simply take continuation of these components, and then I trace. Well, in this picture, it is all connected, but it's not supposed to be. Yeah. So in this way, I can define with the help of omnial picture. I can identify irreducible analytic components, and this is a statement that says that in every model, for quite simple reasons, there are you have this decomposition into analytic components, and the number of analytic components is at most countable. So it is an important property that makes a difference between profinite completion and the actual analytic picture. That if you try to do similar operation in the projective limit, you see, you can, instead of this process, you can look at finite levels how algebraic varieties split. And so if they start splitting into finitely many, then you get continuum many. But here, or minimality keeps the picture, just you have a countable decomposition. Yes, and then there is also an important statement that when you take this one of these components and push it down, then and this component being irreducible, then what you define, what you find out that its image is well, actually, I should have added here, it is an irreducible algebraic subset, well, the risky subsets of this, and then again you can keep a trace of what number field might be needed to define it. Okay, so now I define define my structure. So for each of the model of this subminimal theory, I look at the cover and everything. Yeah, because in this picture everything is definable in my R. Everything is interpretable in my R. And so I take my cover with, of course, with this covering functions and all the algebraic sorts, and that's what is the structure that one of the structures that make up my class, my abstract class. And the language that I choose for it is the one that was explained in the previous slide. So it is language of these primitives. And we just have seen that the analytic components are also primitives, but they might require bigger fields to for the definition, the component. And so I work now in this much smaller language, and this small language it forgets about minimality, but what is important, what remains an important tool is that in the minimal structure, I have this notion of algebraic closure or this dependence relation that related to model theoretic algebraic closure. And it is convenient to keep track of what is the corresponding dimension. It's going to be infinite, but well, it's going to be infinite most of the time. Okay. Now, so this statement is just to tell ourselves of what is visible in this very small language, and it is this algebraically closed field K, which is analog of field of complex numbers. It is this covering maps, And yeah, I'm sorry. You see, when I did this introduction of this structure on top, actually, I could have been much more economical and say that it just has one sort, this cover sort. I don't need anything more, and all these analytic relations on it, these primitives on it, and from there I already can get this algebraically closed field K and these varieties and the covers and the points of the little k. And so then model theoretically, what is the most important thing? Well, it is quite dense slide, but let me just help you by saying what is the meaning of this whole thing. So now I'm trying to understand. So if I take my analytic set on top in some m+1 power, and then I can take projection or apply existential quantifier. And the question is whether I can control what is in the projection. So if I do it with in the usual Zariski geometry, then we all know what happens. So we'll get the image of Zariski closed set is constructible, or more precisely, it is, well, if we take an irreducible Zariski closed set, then the image is some irreducible Zariski closed set minus small dimension Zariski closed subset. It turns out that the same can be proven here with replacing, so now it is, the image is irreducible. You find some irreducible analytic subset definable in this language, that primitive, and then you take out some smaller dimension, well, countable union of something smaller dimension, and so it is very similar situation. That's what it says. Yes, and now you see what is our situation on the. So how much time do you have? 5 minutes. Okay. So it is a situation now that I'm studying actually some analytic structure, or when I move into non-standard models, some pseudo-analytic structure, and in fact, what I want to know, what are the model theoretic status of this structure. So if I write, say, first order formulas, then you know how far I go from initial analytic sets, and if I know that I don't go too far from there, so for example, by taking projections, then, so some years ago, I introduced the notion of analytic Zariski structure. And this property is one of the requirement of analytic Zariski structures. Other properties are quite straightforward. It is to have a reasonable dimension, and yeah, of course, intersection of analytic Zariski sets should be analytic Zariski. And the important thing is that any analytic Zariski set splits into at most countable irreducible. But this we had from the previous slides. Yeah, so these are sort of difficult parts of it. And so, in fact, what we have proved in the previous slide, or formulated in the previous slide, is a statement that it is an analytic Zariski structure. And being analytic Zariski structure actually means a lot. Okay, so it was actually discovered by Gavrilovich, and I sort of rediscovered and reused it later, that once you have analytic Zariski structure, it is homogeneous over algebraically closed subfields. It is, yeah, Aleph not homogeneous. So, which means, you see, so this is this picture. So obviously, what is locus of a tuple? It is, you know, you take a positive type of this tuple using parameters from K. And so if you have two with equal loci, and you have you added some W here, then you can find another W on this side. So this is homogeneity that we do have in mind, and this takes place in this statement. It takes place if your type is over algebraically closed field. Now, in the theory of abstract elementary classes, the thinking it goes not over you know, subfields or something like this, but thinking is over submodels, and you can convert it into the statement that it is homogeneous over submodels, and as a result of it, if you have enough homogeneity, then it turns out that yeah, if you have two such real models of R1 and R2 are O-minimal models, models of O-minimal theory, and you consider the corresponding structures, then if these models are not too large, well, uncountable, but not too large, then you can build isomorphism between them. So you see the models R1 and R2 could be very different, but the structures are isomorphic because they are in this analytic language. Now, you see, in the case when we work with curves, so in one-dimensional case, much stronger statement can be said. And this statement is that in this case, we actually have that our class of such models can be seen as an abstract elementary class. That means that it satisfies the conditions of Shelach for abstract elementary class. And it is what is called, technically called quasi-minimal excellent. Excellent, well, quasi-minimal is analog of strongly minimal. Excellent is kind of a strong version of stability for abstract elementary classes. and eventually categorical in all uncountable cardinals. Moreover, it can be axiomatized by L omega 1 omega together with a quantifier for uncountable many. And the difference between the theorem on the previous slide with the theorem on this slide is that in one-dimensional case, the remarkable theorem of 5 authors allows us to avoid some difficulties of Shellock's theory of abstract elementary classes. There is, Aleph naught homogeneity is one of the strong assumptions, but then there are some more technical assumptions. And for one-dimensional case, so these guys show that it is enough to have less, and so that's why it works. So that's a general result. And now 2 natural questions. So it looks like you know, it looks quite unnatural that it works in one-dimensional case and doesn't work in high dimension, because also the reason is purely model theoretic. No, I don't want the third question. Yes, and so probably with some effort this can be somehow done. And this is quite important. And this is a challenge purely model theoretic. And then there is this question, whether it can be axiomatized in L omega 1 omega way without Q. Well, beyond this question, you can also ask whether in every case there is what I previously called without explaining what is natural axiomatization. So something natural, meaning that it is a kind of a geometrically meaningful axiomatization, and where geometrically maybe should be sort of in terms of model theoretic geometry, like, you know, something on the, you say that something is locally modular and something else such as this. So that's it. Thank you.